Okay, what we're going to do here is have a really close look at what's going on in the Bedini SSG circuit, where some people are getting confused and thinking that we can get more out of it than we can put into it. So we're going to go through this whole system step by step, and we're going to measure voltages and currents at various points in the system. And you'll see 4 large caps here, and those caps are to smooth out the pulses so our meters will be reading correctly as far as voltage and current goes. So the setup we have is here. I haven't put the trigger coil in or hooked it up to the base of the transistor, not necessary for this operation. The critical thing about building a decent pulse motor is the clean switching of the transistor. You'll see so many people throw them together and toasting their transistors, they're getting hot, blah blah blah. The transistor should stay cold if it's switching correctly. So what you want is a nice clean on and off with the transistor. The best way to achieve this, unlike it states in the how to build a Bedini pulse motor, in this case just the simple schoolgirl circuit, is put your magnets so that the fields are alternating north, south, blah blah blah. This is how I build mine, and after various tests with different rotors of exact same magnets diameter, I found that the alternating fields are the best way to go and most efficient. Most of you use soft iron cores filled with welding rods or coat hangers or something like that. This coil here is the very first coil I ever built for the pulse motor, and as you can see, it's just chopped up bits of coat hanger stuck in there and glued in. A very good coil. But what happens if you use a configuration whereas your coil on the rotor side is pulsing a north field out, and you have all north field out as specified on your rotor, you will find that your core itself will start to retain some magnetism and become a magnet itself. That is when your efficiency will go right down the drain. Best way to stop the core from becoming a magnet itself is to alternate the fields on your magnets, and that will ensure the core remains neutral. The other reason I alternate the fields is because the switching of the transistor is very clean, and once we get this fired up you will see that on the scope, that for a pulse motor it has very clean switching. There's no need for the heat sink. I just stuck it on there, give me something to stick everything on, but the transistor will stay cold. We will take a temperature measurement of that before we start, and then after we've been running it fairly hard throughout the test. So our test points here, we're going to start with our power in, which will be our amps times our volts. We'll be remaining on 15 volts throughout the whole test. We're then going to shift our amp meter here, which is between these two caps, and then we will shift it here, which is between this cap and this cap. Last but not least, we're going to shift it over here, which is between the cap and our load, which is our globe, incandescent bulbs. You'll also know I've got one in between the first and the second cap, which is right here. Those two bulbs are identical, nothing different between them. So and you'll see an interesting effect which is quite explainable once we start our testing. My primary coil is 2.7 ohms of resistance, and as we're going through the test we'll be measuring the voltage across each cap as well. So that's what we're going to do. We're pretty much well ready to go here to start it up initially. So I reduced the resistance on my pot quite low to get it going, and we're simply going to fire it up. The first thing we'll notice is what these two globes here do once we start. So without me touching the pot, you'll hear the motor was dragging on a bit, and then it just boom. So what happened there was we actually went from a couple of pulses in between each magnet down to one. So now I'm going to turn the resistance up to the base. Now you'll see here at the moment, where are we? No good on AC. We'll have to go to DC, of course. Hit the button with getting it all set up. So you'll see at the moment that this globe here is brighter than this one. You may not be able to tell, but it is. I can see that quite clearly. So now we're going to turn up the resistance to the base. Let this motor speed up. Now this voltmeter here at the moment is across the first and the second capacitor, and we're reading the potential difference between those two caps, which is 3.4 volts at the moment. Throughout this test, when we go shifting our multimeter to read current, I'm going to get the potential difference between those two caps identical, which I'm going to get as close to 1 volt as I can, and we'll keep that 1 volt throughout the test, which basically means that we're putting the same amount of current through it because we have the same amount of voltage across our visual resistor, we could call them, light bulbs. So I've gone a little far there. What I really need is a 100k pot after this one, so I can trim it fairly fine. It's a bit touchy. But you don't get much closer than that. So exactly 1 volt across that globe there at 124 milliamps. So that is the power that that globe is consuming, and I don't even know if you can see that. It's got a very slight dull red glow. Our output side is going really good, which means we're putting more current across that globe than we are this globe. And this is pretty much where they get all screwed up with their 1 ohm test. But yeah, incorrect. So as you can see, across that resistor there, we are definitely dissipating more power across that resistor than we are this one. This is where they get all bungled up with their 1 ohm test. Do the 1 ohm test, you'll see there's more power coming out than going in. No, there's not. Because the voltage across that cap is far higher than the voltage across that cap. Anyway, so looking at our switching, you can see for a pulse motor that is very, very clean. Our on time is about 32%. 68% off time. So nice and clean for a pulse motor. We didn't measure our transistor for heat, which we'll do now. 19.2 degrees, which is exactly the same as the metal plate that it's sitting on. Our bench temperature is also 19.2 degrees. And a light bulb we can't measure. And our coil's about 19.6. So it's come up ever so slightly, but pretty much well room temperature. So our power in is 15 volts at 124 milliamps. So this we're going to write down as we go, and now I'm going to switch the camera off because I have to move our meters from position to position to make sure I keep the same meter throughout the whole test, and nothing is going to change. So I'm going to write down our power in, and we're then going to switch and put our amp meter right here. I'll start the system back up, get it back to 1 volt. Potential difference across that resistor there, and that will mean that we are back to where we are now, and keep our test fairly accurate throughout the whole situation. So back shortly, guys. Alright, excuse me, so we've got our amp meter now at test point 2, and as you can see it is exactly the same as it should be, because our current is just flowing through this cap. Well, it's not flowing through it, flowing past this cap, and past this cap, and into our coil. So our caps are giving us a nice smooth, even current flow, so we don't have to worry about our meters being messed up by pulses. And as you can see, they're pretty spot on so far. I did say 100k pot last time, I meant 100 ohm pot, so I can fine trim it, not 100k. Just clear that up. So so far so good. I'm about 0.01 of a volt higher across there. It's very hard to get Mickey Smick spot on with this pot, but 0.0089 of a volt is fairly close, and our current is also within cooey of it, so pretty much the same. Said it's hard to get absolutely spot on, but you're going to get the general idea anyway. Yeah, only just have to touch it and it's jumping all over the place. But we're pretty much well out, what are we, 1 milliamp off of our thing, but we're also a little out now because that's reading high voltage across there. We have a lower current. So we're up and running, and so far so good. Temperature on our transistor is now, can't see, so it's at 19 degrees. Apparently the temperature's come down on the transistor. It is stone cold. Our coil at the moment 19.6 as it was before, and our transistor is actually getting colder than when it was before we started. So cold electricity, fantastic if you believe in that. Now you will notice here, I'll give you a little hint as to what's going to happen next when we put our amp meter here, which is just next in line on the way to our coil. You will see here the 5 volt divisions. Now my yellow trace is across the coil itself. My blue trace is across the voltage being supplied to the system. And you can see it's 14 volts RMS on channel 2. Don't forget we have lost 1 volt here across our resistor. 14 plus 1 is exactly 15. But you will see across the coil during our off time, we have about 18 to 18.5 volts. You'll see it flicking up to 19.4 because it occasionally reads a tiny little spike there that's not getting swallowed by our cap and resistor. But about 18.4 to 18.6 volts across our coil, even though we're only supplying it with 15 volts. So I'll let you think about that for a little while, and it's quite easy to work out if you look at how the system is actually wired up altogether, the SSG circuit. So what we're going to do now is switch this back off, and our amp meter is now going to go in test point 3 here. So we'll be back shortly. Okay, so we're up and running again at test point 3, which is right here. We are still at our 15 volts of course, and very close to 1 volt potential difference. So 2 caps all across their globe. Now here's where shit happens. Our negative side from this cap to this cap is of course negative to negative, and our positive is going through our current meter into the positive of this cap, just the same as we've done there and on the input. But now we have 346 milliamps flowing at the voltage of that cap into this one. So now if I remove my voltmeter, now that we know that we are where we were at before, and I put it across this cap without hitting the rotor, like so, you will see we have 14 volts minus the 1 volt across there equals our 15 volts. Our scope also says we have 14 volts RMS. But now we're flowing 14 volts, 346 milliamps into this cap which is driving the motor, when we only had 124 milliamps at 15 volts going into the system then from cap 1 to cap 2. So that 14 volts at 346 milliamps is actually flowing from that cap to this cap. So amazingly, we've more than doubled the power flowing from that cap to this cap than we have flowing into the system itself. So once again, that's our test point. We've done test point 1, we've done test point 2, and we've done test point 3. Now, even though our positive lead remains the same all the way through, and our negative is all common ground throughout the system, somehow we've managed to more than double the power flowing from cap 2 to cap 3. Turn that back on. So now our wonderful pulse motor is now running on twice as much power as what we're putting into it, right? Well, no, not quite. So we'll have a look what's going on very shortly. Once again, we'll get our temperature gauge and shoot that transistor, and at 19.4, so back up where it was before. It does cool down very fast sitting on this heatsink, but so we're rising about 0.4 of a degrees. This thing, well, you can see the current flowing through it, or the power flowing through it, which is our 14 volts at 346 milliamps. The reason it stays cold once again is because of the very clean switching. Once you get transistors that slowly come on and slowly go off, then you run into all sorts of dramas. They get hot and they cook. So yes, it's very possible to get a standard NPN transistor to switch very cleanly on a pulse motor and stay very cold, regardless of the amount of power you put through it, which is way below what that transistor is rated for. That is a tip 3055. Alright, so now we're going to move on to our last test point, which is test point 4, and that is the current flowing through the globe, the voltage across it, and that'll give us what this globe over here is dissipating in the way of power. So once again, we'll be back shortly, and that's going to give us a few answers to the amount of power flowing through here. Right, so we're back to our 1 volt across our globe there, resistor, and we are still at our 15 volts. So we are running as we have been running throughout the test. Now, we have our ammeter hooked up here. We'll take this voltmeter and we'll put it across the other cap. And you'll see at the moment we have 228 milliamps across that U globe, flowing through that globe. 228 milliamps of current. Oh, and I just dropped the clip in the rotor. Not to worry. So, let's have a look at the power being dissipated by this globe here. Alright, so 228 milliamps at 3.54 volts. That is what our globe is dissipating. Now the current doesn't just disappear. You keep an eye on this amount of current. You subtract it from the current we had on test point 3 here, and you're pretty much all going to end up with the current we had in the beginning, which is 124 milliamps. The reason for this is because this circuit, the way it is set up, you have the positive side of our 2 run caps here, what would be the run battery, hooked up to the negative side of what would be the charge battery, and then the positive side, of course, is coming from our inductor. So what you've actually done is you've performed one big current loop through the system. So this meter here is not only showing us the current coming in from the power supply, it is also showing us the current flowing through our globe as well. And this is where the answer comes in. How come we've got 18.6 odd volts here? Because it is our supply voltage, which is 15 plus 3.5 volts gives us 18.5 volts, which is pretty much what it is. So the coil, because of being it's a current loop in this situation, is also seeing the voltage when it is switched off of our supply voltage plus the voltage across the cap. Yes, and that is equal to the voltage the coil is seeing, or is across the coil when the transistor is open. So there's some facts, and that is the tomfoolery, the guys that try and sell these U-Boot handbooks and everything, the secret pulse motors. There's no secret. You've simply made a big current loop, and the 1 ohm test is just a bullshit test, because of course we've got the current being dissipated through our load, plus the current flowing in from the supply, all marrying up together at this point here. So there you go, 1 ohm test. They tell you to do the 1 ohm test, load of rubbish. If they tell you there's more power flowing through the system than what's going into it, well, there is in a sense, but it's just a big loop, and it's power that you cannot use. So our total power in is 15 volts at 124 milliamps, will give us our watts, and our power out of the system in the way of heat and light is 228 to 229 milliamps at 3.55 volts. So from these numbers we can calculate the efficiency of this pulse motor, and I would be surprised if it's in excess of 50%. So there you go. Not a lot here to explain other than what we've just witnessed. No magic happening. Right, for some reason our transistor has once again come down in temperature. Seems to go up when you first start it. That's probably because I drive it pretty hard, then once I've tuned it, it actually comes down in temperature. Our coil is now 20 degrees. Our bench is 19. Our transistor is 19, so we can pretty safely say that very little power is being dissipated by the transistor. A very small amount as far as heat goes by our coil. The bulk of it is resistive losses. We've got 4 big large caps here, they're not going to be helping much, and but the bulk of our power that's dissipated from the system is being dissipated through that globe. There will be a bit through our trigger circuit as well via this resistor and the coil around the former there for the trigger, a little bit for the diode, but all in all the system is running at a pretty good loss. So yeah, there's absolutely no magic in the good old SSG pulse motor. It's all just fables and tricks they use to try and convince you to waste a bit more of your money on their lovely books and what have you. The secrets too, there is no secrets. It's all there right in front of you, you just got to look. Alright guys, thanks for watching, and we'll see you next video. Cheers from the Tin Man. Alright, so how did we go with our efficiency? Well, our power in was 15 volts at 124 milliamps, which is 1.86 watts. And of course our total power out is 1.86 watts when we take everything into account, heat and all that sort of crap. A bit of mechanical work being done by the rotor, shifting a little bit of air, but what goes in must come out. And so basically, no matter how you build your pulse motor, it's always going to be 100% efficient when you take everything into account. As far as electrical output goes, which was our 2 globes, this one was putting out a small amount of light and heat, so that is an output. As far as electrical output goes, that was 1 volt, of course, at 124 milliamps, which is 124 milliwatts. Globe B was 3.54 volts at 228 milliamps, which was 807 milliwatts. So the 2 globes added together is 931 milliwatts. We times that by we divide that by our input power, which is 1.86 watts, 1860 milliwatts. Times that by 100, we get our percentage of efficiency for electrical output, and it was actually 50.05% efficient. As far as our electrical output goes via the 2 globes, which is a little better than I thought it would be for a quick throw together job, but the clean switching makes a lot of difference. I no doubt could get it a little better than that. But yeah, that's what we have, 50.05%. Now, the current we've seen from cap 2 to cap 3, with the power flowing through there, that current was 346 milliamps. Now if we take off the 228 milliamps that was in our current loop, we have 118 milliamps, which is only 6 milliamps short of our input supply. And looking at those 4 big caps there, I'm pretty sure you know where it went. And also we did not take into account the trigger coil and the power being dissipated by that across that resistor, or the 100 ohm resistor here. So we have made up for our 6 milliamps there in power dissipation across the trigger side of the circuit that we did not measure. But yeah, so there you go. There's no bloody secrets to pulse motors, so don't go buying books wasting your money on the secrets to pulse motors, because it's all crap. and you can't do it much better than this with large smoothing caps to get very accurate readings of really what is happening within the good old SSG pulse motor. They will argue about it, they'll tell you, oh, that's crap, but one thing they will never do is show you one that is producing more power out than what you are putting into it. Thanks for watching, guys, and I just tacked this on the end of the video, the results. I'm sure you can add them all up yourself if you want to, but they are the facts, and that's how your SSG pulse motor works. Cheers, guys.